Alright, so previously for the discontinuity functions, we said the basic form is of this way, plus or minus, and then magnitude of the load, right? And then we have Macaulay bracket, we have x minus a, x, and then n, right? And then we specify what each of these mean. We were like the positive, negative here depends on the direction. And we said generally the convention I've been using so far is for force upwards, for force, right? For force upwards means positive, and for this one the corresponding moment this way, moment, this is positive, right? Okay, and then we specify the x, which we said is constant, and we said the e is where the load is, the position of the load, right? Or if it's a distributed load, where it starts, this particular e here, right? And then we said the n depends on either whether it's a moment, whether it's a load, whether it's a uniform distributed load or linear distributed load. We give them values, this -2, -1, 0, and 1, right? Okay, but then there's something that we should be very clear of. There are times where, especially for this one, for the distributed loads, right, for these two, there are times where we have to be very careful of what we put at the e. Are you okay? The assumption for this whole thing is that whenever you put a particular e here, meaning from the position it starts, it gets to the very end. Are you okay? So if we take this example, for instance, this very one here, if I specify a particular e, so let's write the load equation for that one. Now we know the basis. Now let's try to write the load equation. Are you okay? For this particular one, and then we'll come back. So if I'm trying to write the load equation here to be w, have a w x, right? And then at the point, so I'm starting from the origin, right? So the first one I'll meet is, let's say the 75 is a point load, right? So 75, and then it's actually coming down. So let's do the direction first. It's coming down, so negative, and then 75, right? What do we have in the bracket? X. Where does it start? Its e is at 0, right? And it's a point load, right? So p is what? -1, right? And at that very point again, that's at the origin here, I have something else that starts there, which is a more a uniform distributed load, right, which is going up, so that's positive, right? And then I have a 35, which is the magnitude bracket, and I have an x, right? Where does it start? 0, right? Okay, and it's uniform distributed, right? So that's 0, right? When I move on, right, in this direction from the origin, the next one I meet is this 60. It's pointing down, so minus, let's bring it down, -60, minus, because of direction, 60, the magnitude bracket, x. Where does it start, or where is the position? That's 2.5, and it's a point load, mp, so that's -1, right? Let's clean this. What else do we meet as we move on? At this point again, we're having a moment, right? Looking at conversion, we said this way is positive, right? Okay, so then this one is the same direction as our positive. So we are saying the moment there is positive. Okay, if it's positive, let's see, this way goes this way, so that's positive. So our moment is positive, right? The magnitude is 120 bracket x minus what does it start? What's the position? 2.5, right? And then it's m, so that's -2, right? As we move along from this side and we move on, what else do we meet? We don't meet anything else until we get here, where we end up with a reaction because of the support here, the fixed support here, right? So that's acting up, so that's a positive, right? The position, we don't know what it is actually, so let's say the magnitude is dy, right? Now you have x minus, what's the position? This plus this, that gives us what? 6, and it's a point load, right? So that's a -1. right? So for this particular one, it makes sense if you write everything this way. Are you okay? But then we'll come to this and then see the difference, because our aim right here is about the section of the loads, right? Because when you look at this particular distributed load, for the point load, it's fine. Where they are, that's where they are. It's just a point, right? It doesn't matter where they are. So they're just points. When you represent them once, that's it. But for the distributed loads, especially this one, this here, the one in yellow, right, is distributed. So like, where's the equation for it? The representation of that one, where is it? It's 35, right? So there's it. So then what happens is that so whenever we turn it on, right, so whenever we start it like this, right, we actually start at at x is equal to 0. So that's what we've represented this minus 0 here, right? Because we said we have plus or minus this x minus a, right, and n. So we say the a is where it starts, so right, so if we put 0 here, that's where it starts. But then for this particular one in yellow here, it ends at the very end of the beam. So it's fine if you represent it this way. It's fine, completely fine, it makes sense, right? But when it comes to this particular example here, a minute. So now we are done with this, and then we know the representation is clear now. So now we are here, the right hand side, right? But when it comes to this one here, what happens is that when you look at the distributed load here, it's not acting on the entire beam. So like, if I decide to do this, let's see. Let's write the load equation for this one. Right, so we are starting from the origin. With this diagram is somewhere here. So W X, right? What's the first load that we meet is this one. It's going down, so minus, and then have 52 magnitude to bracket x minus e. Where does it start? 0. It's a point load, right? So that's minus 1. Are we okay? Minus 1. Seems I end here. Minus 1, right? As we move along, what's the next thing we meet? We meet two things here actually. Let's make this clear. Because we've not found the reaction force and everything, it's a bit some way, so I'll just be using representation too. So we are here, right? So now we move and we are here now. So we meet two things. We meet B and then the start of this distributed load, right? So let's write the B first. The B is actually up because it's a reaction, so that will be plus, right? The magnitude of B, right, is a point load, so x minus what does it start? It starts at 3. X minus 3. The exponent, because it's a point load, is what? Minus 1, right? Minus 1. Minus 1. Are you okay? And then what else starts at that 3? We have the distributed load, right? So that will be, let's bring it down. Actually, it's pointing down, so that's a minus, right? So minus, the magnitude is 35, right? And then bracket, Macaulay bracket, x, it starts at where? 3. And this is a, what do you call it? It's a distributed load, right? Uniform distributed load, so that's what? 0, right? So we move along until we get here. What do we have again? We have a D which is pointing up, dy. Let's bring it down. dy is pointing up, so plus dy, and then we have x. Where does it start? This plus this plus this, that gives us 12, right? 12 is a point load, so that's minus 1, right? Then we move on till we get here, right? So in actual sense, we've dealt with this one, the distributed load, but I'll come back to it. So then the next one we have is this, right? It's pointing down, so that is minus, and then you have what? 36 in bracket x minus what? Where does it start? It starts at the end, which is this plus this plus this, right? So it's 12 plus 3, that makes it 15. It's a point load, so the exponent is what? Minus 1, right? But then there's a problem with the distributed load. So let's see. You see, for the distributed load in this example here, it starts from the beginning and ends at the very end of the beam. So it's fine if represented with this alone, right? But for the distributed load here, in fact a uniform distributed load here, what happens is that it starts somewhere and doesn't get to the very end. It ends before the end of the beam, right? So in actual sense, what we've written here, what is it, 35, right? What we've written here is saying that it should be something of this sort. It starts here and then gets to the very end here. That's what we're saying, right? So meaning that we have to turn it off at some point, because like this equation here is representing everything from here to here, right? So meaning we have to do something to make sure that something is countering this portion here, so we get something of this sort here. So let's see. So that's why we see the switching of the distributed loads, turning them on and off, a lot of times, but this is the concept behind it. The equation representing the turning on, this one here represents turning it on from here to here, but then the actual thing is from just here to here. So that's what we do. You put something here, right? That's on the that what they call having an opposite direction to the actual thing up there, right? So this, 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 this. Let me write it up somewhere so it's clear. So it's saying that the actual beam distributed load is this way, right? And end here. But the equation I've written suggests that, says that we've actually turned it on from here and then it extends up to this side, right? To this side. But then we need something, so let's complete this one. The red is representing the equation I've written, the yellow is the actual thing. So in order to make sure that we've taken this side off to make sure it's the same as the yellow one, we bring something to counter it. And how do we do that? We do that by introducing something else there that's in the opposite direction to the rest of the red that we don't need. So something of this sort. So we are just assuming that our beam is about here. We are assuming that this is our beam. So let me bring a line here. Okay, so we are assuming the blue is our beam. Okay, so we are bringing something here to turn it the rest off, something to counter the rest of it, right? So that's the whole thing of switching on and off distributed loads, right? So now that we get this, we have to make sure we have an equation that actually represents that. And how do we do that? Just the same thing. We said that the basic element for the singularity function is what? Plus, minus, right? That depends on direction. Magnitude of the load, right? Now you have Macaulay bracket x minus a, which is where it starts, and then n depending on the type of the load, right? So this right here. So now we are going to write this in terms of an equation, right? So let's do that. Let's see. Okay. So this is what's happening. We first of all know that we know the magnitude. Then again, the magnitude will be the same as that of the original one. So, but we know it's in the opposite direction. So that's the first thing. So we are putting it close to its relative. So let's see. Let's make it green. Yeah, so it represents what we are doing. So it's opposite, right? So if this is minus, this will be plus. So plus, right? The magnitude is what? 35. Let's make it smaller so it fits. So it's plus, right? The magnitude is what? 35. And then inside the bracket we have x. Where does it start? It starts just at where the other ends. So that's 3 plus 3 plus 6. That's 12. Minus 12. Oh, let's see. Minus 12. Okay. Minus 12. Okay, minus 12. And then there's a distributed load, right? Uniform distributed load. So that's 0. So you see, it's just the same thing, but we've counted it to make sure that it exists within a particular range. So you see, this one starts at 3. And then this equation here means that it turns it on up to the end of the beam, right? but then it ends at 12, right? So because it ends at 12, we have to bring something that's in the opposite direction. So just the same thing. So we have minus, this is plus, right? Minus, this is plus. And then where this one starts is 3, where this one starts is 12. So that's the only thing that makes them different. Okay, so this is it. All right.